Yes, Professor Jayant.
Mm-hmm.
Uh, I have set up the another YouTube share means what you said live streaming. The scheduled one there is some problem. I'm not finding it right now. So I have another live I have started.
Okay.
So I'll start in. So Professor Jayant, shall we start now?
Yes, certainly.
Yes.
Hold on 1 second.
Yes.
Give me 1 second.
So, hello everyone. A very good morning to you all, and I welcome you all to the first live event in my YouTube channel. And well, today, today, today it's Easter Sunday, and we would not get any other special day than this to start this wonderful event. And we have one of the eminent astrophysicists with us, Professor Jayant Murty, who is a senior professor at Indian Institute of Astrophysics, Bangalore. So viewers, I would love to tell you more about Professor Jayant and his contribution. Prior to joining Indian Institute of Astrophysics, he received his PhD in physics from the Department of Physics and Astronomy, Johns Hopkins University, USA, and later joined as a research scientist in the same. His research revolves in the space mission, starting with the payload on the space shuttle and interstellar dust and diffuse radiation field studies and many more. It's worth to mention that Professor Jayant is one of those prominent scientists of the country who is popularizing science and uh, space work among the common folks for this deep and better understanding. So it's very fortunate for me to welcome you, sir, Professor Jain. Thank you so much for coming to my channel for the special talk for the school students and the college students out there in West Bengal and all over India and the world. Thank you so much, Professor Jain. Now it's over to you, the whole session. For you.
Okay, thank you. So shall I share my screen now?
Sure, sir, sure.
Okay, that is coming okay?
Yes, Professor Jain.
Excellent. Okay, so I will go ahead and start. I'll try to finish in about, let's say, 30 to 40 minutes. And then maybe we'll, okay, let me go ahead and start. So what I'm going to be talking about is space astronomy. And so when I start with space astronomy, it's always a good thing to tell you a little bit about the people involved. So we couldn't have space astronomy, that is astronomy from space, without going into space. And of course, people have talked about going into space for forever. It's been you had Jules Verne from the Earth to the Moon, Kepler, who had his I think again people going to the moon, but you couldn't do it. You couldn't talk about it in a practical sense until the equations were worked out, until the scientific and technical feasibility was shown. And the first person to do this was Tsiolkovsky in what was then Russia. And he was the one who who wrote down many of the equations that govern spaceflight. Now, this was followed by other people. Amongst the most prominent of them were Robert Goddard in the US. He was the pioneer of liquid-fueled rockets. Werner von Braun, who got his start with the Nazi Germans, his job was to build V2 rockets, which were intended to bomb London. And when it was clear that the Germans would lose the war near the end of the war, the SS sent an assassination squad to kill him, but he escaped with his team and he gave himself up to the Americans. The Americans took him to Huntsville, Alabama, and what is now the Marshall Space Flight Center, and they just told him to continue working on his rockets. And he was, as I'll show later, he was responsible for the first American satellite, for Explorer 1. On the Russian side, on the Soviet side, there was Sergei Korolev, and he was responsible for that entire series of Russian successes, from Sputnik to Laika, to Yuri Gagarin, to Valentina Tereshkova. A whole series of Russian firsts. When the Russians were actually the Soviets, they hid his name because they were afraid that the CIA would try to assassinate him. And so he was only ever called the Great Designer. It wasn't until after the fall of the Soviet Union and the declassification of many of the Soviet files that the scale of his contributions were understood. On the other hand, with Werner von Braun, it's now becoming understood that the depth of his involvement in the Nazi effort, the space program at Peenemünde, or the V2 program at Peenemünde, was founded on Jewish slave labor, and von Braun had denied knowing much about it, but in fact he was responsible for, or he knew how much of the tunnel digging and so on was done by Jewish slave labor. So the space age began with Sputnik, and this was October 4th, 1957. It was a football-sized object, and it was launched by the Soviet Union, and it went around the world. That's all it did. It went around the world, and it beeped, so that anyone with a ham radio set could hear Sputnik. They could detect the radio signals coming from Sputnik. Now, of course, this was the middle of the Cold War. At the Russians and the Americans, the Soviets and the Americans, were in constant competition for the hearts and minds of the rest of the world. And one of the things that they were competing with is access to technology. And so the Americans thought they were comfortably ahead. And but nevertheless, there was this constant fear of nuclear warfare. And so this guy here is Bert the Turtle. And he's got you can watch his video on YouTube. But basically what he says is that anytime there's a nuclear attack, you have to duck and cover under whatever is available. Bert the Turtle could cover in his shell, but if you were in a school, you could duck under your school desks. If you were out in the open, you could duck into a doorway, cover yourself with newspapers. Of course, now we know that none of this would have helped much in the case of a nuclear attack. But still, this was the times. It was the 50s. And so when Sputnik was launched, it was a major blow to American prestige, that suddenly the Soviets showed that they were better. They were smarter. They were more technically advanced. They actually had something launched into space. And so this caused the Americans to suddenly put a lot of money into everything to do with space research, anything to do with aeronautics in general, but more specifically, anything to do with space research. And so immediately after Sputnik, they tried their own program. And this is the Vanguard program.
A large segment of the nation's scientists, engineers, and production experts were drawn together and given direction. Against this background, the country carried out a series of space experiments that yielded valuable data to the world's store of scientific knowledge. There were a number of failures during the year, and the United States promptly announced them. The first and most spectacular of these was Vanguard at the end of 1957. There were other Vanguard failures.
So the first attempt was made by the Navy with the Vanguard program. But as you see, the Vanguard program was not very successful. Rockets are supposed to go up. This one went down, didn't even get off the launch pad. It just collapsed in a glorious ball of fire. And so then they gave it to Wernher von Braun. And Wernher von Braun and his team launched the first American satellite, Explorer 1, from Huntsville, Alabama. And then but as I had said, the Soviets were still doing first in everything. They were they launched the first the first man into space, the first woman in space. Everything was done first by the Russians. And so Kennedy, who had just become president, wanted to know what the Americans could do that would make an impact and would show that the Americans were still advanced, were more advanced than the Soviets. And so what he came up with was the Apollo program. That before the end of the decade, we shall land a man on the moon and bring him back. I note parenthetically that when he said man, he meant man. This was in the 60s. There was still no women's equality. And so he really did mean a man on the moon and back. Despite Valentina Tereshkova, it was not until Sally Ride in the 1980s that women became an active part of the space effort. And I'm happy to see that Artemis now has a more diverse crew. It's not only white men, as was the case earlier. I am disappointed that Gaganyaan, the Indian manned program, is really only men. It should really have been a crewed program where they could very easily have picked women to be part of that first flight crew. Their argument is that they wanted test pilots, but you don't need test pilots to do space missions. After all, Laika the dog went up into space, Ham the chimpanzee went up into space. There's absolutely no reason that they could not have selected several women as part of their initial flight crew. So the Apollo program began with the single man Mercury program, in which the first American into space was Alan Shepard. He went up and came back down. The first American to orbit the Earth was John Glenn. And then after that, after the Mercury program came the two-man Gemini program, and then the three-man Apollo program. So this particular one is Apollo 8, and the Apollo 8 astronauts were Time Men of the Year. So they went around the moon and came back. They did a figure 8 around the moon. They were the first people to see the far side of the moon. This picture, this photograph from Apollo 8, then became a canonical picture for the environmental movement. Because what it shows is that all of humanity, except for those three men in Apollo 8, are in this picture. Every single person, except for those three, alive at the time, 1968, is in this picture. And this is the famous big blue marble. Below it, you see the moon what Buzz Aldrin was later to call the magnificent desolation. And what this picture shows clearly is that we only have one place to live. The only place we have is the Earth. We're doing a fine job of messing it up. It seems almost impossible for us to keep the global temperature rise under 2.5 degrees. And so this is just today I read that the oceans have reached another new record high. And so when we think about setting up bases on the moon, setting up bases on Mars, that may be as may be. But the fact is, for all of humanity, except for those very few people, the Earth is all we have. And we need to do our best to keep the Earth livable. Now, after Apollo 8 came Apollo 11, and that was Neil Armstrong landing on the moon. This particular picture is Buzz Aldrin. There are very few pictures of Neil Armstrong because Buzz Aldrin, like some other people we know, liked to have the camera on himself. And so here he is with the American flag. I'll just have one slide on this. This is, many people ask, why, are we sure that people landed on the moon? And to that, I always point them to this website, www.badastronomy.com, because there's so much good science in the world that it's kind of silly to even think about the bad science, to waste any time on the bad science. Let's focus on learning the good science. And so this is the famous flag waving. If the flag is on the moon, why does it look like it's waving? And it's not waving. It just looks like it's waving because when they extended it, the spring broke part of the way and the flag didn't extend out all the way. So it just looks like it's waving. It's not. So that was one particular aspect of why we go to space. The whole thing was a political show. And it was a space race. It basically ended with Apollo 11, a few more Apollos, Apollo 17, but it ended with Apollo 11 for all practical purposes. We're still going into space, but a lot of the reason we go to space is for commercial reasons. So here is a weather photograph, 5 cyclones off of the eastern coast of India. Here's a picture of Bangalore, a photograph of Bangalore from space. Again, remote sensing. And so there are many commercial reasons to go into space. One of the most important now is GPS, the Global Positioning System. When you order from Zomato or Swiggy, you have, they use GPS to figure out where you are. When you call a taxi, whether you're at home or somewhere outside, the taxi knows where you are because your phone tells it. Your phone has GPS on it. The cabbie has a GPS on their phone. And so they know how to go from where they are to where you are. So all of these are commercial applications. Military applications, of course, always nice to have a spy satellite above that will constantly tell you what's going on below. But again, these are not what I want to talk about. What I want to talk about is astronomy. Why do we do science from space? So before we even ask why we do astronomy from space, we should ask why we do science from space, or why we do science at all. And this is not an obvious question. Many people say we do science because the science of today is the technology of tomorrow. But really, that's not why we should do science. We should do science, and we should justify the way we do science just because we're human. Because we're human, we have curiosity, we want to teach rationality. And so the reason we want to do science is because we want to learn about the universe. And that's important to us. In the same way that we watch movies, that we listen to music, we watch a dance program. These are all part of what makes us human. And the central drive in humanity is the desire to learn more about the world around us, about the universe around us. And so I feel that it's important to do curiosity-driven research. Again, I can talk about the economic benefits of doing research. India spends 0.7% of our GDP on doing research, basic research. The US spends anywhere from around 2.5%, 3%. China spends 2.5%. And so when you spend much more money doing research, you will, of course, do much better research and much more research. Now, given that we think that research is important, why do we go into space at all? Why is space important? And there's a lot of reasons not to go into space. Here you see the FUSE satellite being launched on a Delta II rocket from Vandenberg Air Force Base. And you can see that it's obviously expensive. The spacecraft itself is a relatively light, maybe 200 kg object on the top of that of the rocket. So you're wasting so much fuel, such a big rocket to send up your little satellite into space. And so you're obviously wasting a lot of money. It's expensive. $200 million, $300 million. The Hubble Space Telescope was maybe $5 billion. JWST is maybe $10 billion, $10 billion. So it's all expensive. And once you send it up there, there's no room for mistakes. You can't go and buy a transistor from City Market, because if your transistor fails, your entire payload fails. And then you wasted all that money. You can't upgrade your mission. You go up there, that's it. Your telescopes get bigger, your detectors get better. But in space, there's nothing you can do. So why do we go into space at all? The first reason is because the sky is actually opaque over most of the electromagnetic spectrum. My own area, ultraviolet astronomy, you have to go above the ozone layer. X-rays, gamma rays, all of this, you have to go above the ozone layer. There's some areas, some windows. From the ground, you can look in the optical. You can get the radio. So you have these big optical telescopes. You have the big radio telescopes, GMRT, for instance. But in order to do much of infrared, you have to go above the water. So maybe you can do it from a high mountain, but if not from a high mountain, you have to go to space. JWST goes to one of the Lagrangian points where it's very cold. So you have to get above the atmosphere. Otherwise, the atmosphere will block a lot of what you see. Now, the reason that you need to observe other parts of the electromagnetic spectrum is because the electromagnetic spectrum is nothing but temperature. As you go from the shortest wavelength photons, gamma rays, the highest energy, shortest wavelength, to the lowest energy, longest wavelength photons in the radio, you're going through the electromagnetic spectrum, gamma rays, X-rays, UV, visible, infrared, radio. You're going through the electromagnetic spectrum from high temperature, gamma rays, to low temperature, radio. So when you look at gamma rays, you're looking at the highest energy parts of the universe, the hottest parts of the universe, black holes, supernovae. When you go to the radio, you're looking at the coolest parts of the universe, the 3-degree microwave background, for instance. Infrared is important for looking at planets. The Earth has a temperature of 270 degrees Kelvin, and so it radiates in the infrared. So if we want to detect extrasolar planets, one of the best ways to do it is in the infrared, as does JWST. So JWST will look for exoplanets and will look for exoplanet atmospheres. Another reason to go out into space is because the sky is bright on the Earth. In any big city, I'm in Bangalore, in Bangalore, typically what you say is that you see 6,000 stars. But in any big city, you're lucky to see 100 stars. And so you really have to go out of cities in order to see the dark sky. Most of the big telescopes are on the top of high mountains. Firstly, because they're dark, far away from cities. And secondly, because they're above much of the water. But, and this is clearly shown from this picture from the space station, where the astronaut just pointed a camera out the window and took a picture. And so here you see the Orion, but Orion's feet are entombed in the muck of the atmosphere. Atmosphere is just bright. So if you want to see really dark fields, you have to go above the atmosphere. The atmosphere also causes twinkling because you have a constantly changing index of refraction along the line of sight from us to any star or any galaxy. And what this constantly changing index of refraction does is it changes the brightness and the position of whatever you're observing. So it blurs out your image. So you see here that in this picture on the top left, you have the galaxy NGC 4314, and you're observing the center. That central box has been blown up into this photograph from the Hubble Space Telescope. And you can see how much more detail you see. Once you see more detail, now suddenly you know more about what's going on. You have higher resolution, and you can see the details of what's happening there. Those of us who wear glasses, if you take off your glasses, you hardly see any detail at all. Everything is blurry. But now if you put your glasses back on, now suddenly you can detect faces, you can see details. And this is what a telescope does, or this is what going above the atmosphere does. It suddenly tells you that there's a ring of star formation around the central dusty disk in this galaxy. All right, now the first space missions were done by captured V2 rockets. Remember, I told you that von Braun gave himself and his entire team up to the Americans. So he was captured by the Americans, and they took a lot of the captured V2 rockets to the US. Almost immediately, they started using these rockets for astronomy. So you launch a rocket, you get above the atmosphere, and what they did was they looked at the sun, they looked at ultraviolet stars, they looked at comets, anything that you couldn't do from within the atmosphere. And they did a lot of new things. Anytime you're looking at something for the first time, you will always make discoveries. So they discovered ultraviolet emission from the sun. They discovered these molecular lines in comets. They discovered interstellar hydrogen. They discovered X-ray stars. All of this they did for the first time from sounding rockets. But the problem with a sounding rocket is that it goes up and it comes down, and you only have about 5 minutes of time at the top of its orbit where you can actually do observations. So when satellites came around, now suddenly you had a new domain of astronomy open up. You could launch heavier missions or heavier instruments to space and have them stay there for years. And so this particular satellite that I'm showing here is the International Ultraviolet Explorer, but there were many more, and most of these were from NASA. NASA always had science as one of its key drivers. And the reason they do this is because it's always scientists who want to do something new. Engineers just want incremental improvements because they want to make sure that things work. But scientists always want things that are much better than previously. And so much of the technology in space has been driven by science goals. And so here is a list of all of the science missions done by NASA. I'd encourage you to go and look at, search for the science missions. You can click on any of those links and it'll tell you more about what that mission does. And you can even download data from that mission. But I can't talk about all of the science done from space. So I will just focus on a handful of examples. And these are all things that you cannot do from the ground. You can only do these from space. So the first thing I'll talk about is COBE, the Cosmic Orbiting Background Explorer. And this particular spectrum got a Nobel Prize. The reason it got a Nobel Prize is because what you're looking at here is the spectrum of the universe. By spectrum, what I mean is intensity. You're looking at intensity as a function of wavelength. You're getting different wavelengths on the bottom, and you're getting the intensity at each of those wavelengths. And the importance of this curve is that it tells you this is a black body curve. Don't worry about what a black body curve is, but this tells you that the temperature of the universe is 2.725 degrees Kelvin. And that's the importance of a black body curve. There's a unique black body curve for any temperature. And so this curve tells you that the temperature of the universe is 2.725 degrees Kelvin. So what are you seeing here? You're seeing leftover radiation from the Big Bang. When the Big Bang happened, the universe was small and hot. Now the universe is large and cold. So what you're seeing is leftover radiation from the Big Bang. And really the only way you can get this perfect black body spectrum is if the universe started in a Big Bang. So this is evidence for a Big Bang. So John Mather got the Nobel Prize for this particular spectrum. Now here's an image that was actually done in the visible. And remember, I told you that you get much better resolution in the from space. And so what they're looking at here is the Eagle Nebula. And what you're seeing in those nebular clouds, in the giant molecular clouds, you see these red stars. And so what these red stars are, they're actually not red stars. They're actually blue stars. The reason they look red is because you're looking at it through so much dust. And so that dust will absorb and scatter the blue radiation, blue radiation in preferentially. And so all that's left is the red light. Same way that when you see the sun down on the horizon, it looks very red on a dusty day. And the reason is because the dust in the air will scatter all the blue light away. So these stars, they're actually not red stars, they're actually blue stars. The reason they look red is because you're seeing them through so much dust. And so these are stellar nurseries. What you're seeing are large blue stars, young stars, a few million years old, 5, 10, 20 million years old. And so these are stellar nurseries. These are where stars are being born. Our own sun, 4.5 billion years ago, was born in a similar environment, in a molecular cloud. Here's another spectrograph. And what they did is that they put the spectrograph across the center of this galaxy, M84. And so what you see as you go from top to bottom is that you see that the color of the light that you see that is observed from the galaxy, far away from the center, it's green. That means it's neither red shifted nor blue shifted. As you get closer and closer to the star, suddenly the light becomes blue shifted. What blue shifts light? Well, it's the stars coming towards us very fast. If the stars are coming towards us very fast, then the light is shifted towards the blue. If the stars are going away from us, then the light is shifted towards the red. In just the same way that an ambulance coming towards us, the frequency is shifted higher. Ambulance going away from us, the frequency becomes lower. And so, what we're looking at here is we see that the stars are from here, we see that the stars are going away from us very fast. Are coming towards us very fast. Here on the other side of the center, the stars are going away from us very fast. This is basically Kepler's laws. It's the same thing that happens in our solar system. And so what it tells us is that there's an object of maybe 10 million solar masses right at the center of this galaxy. And the stars are orbiting that black hole, that object. You have tens of millions of solar masses in such a small volume. And so what it tells us is that there's a black hole at the center of this galaxy. And I'll show this with the picture, with the image from our own galaxy. And this Reinhard Genzel and Andrea Ghez got the Nobel Prize for a couple of years ago for mapping the motion of stars around the central black hole. And so the cross is where the black hole is. And you see that as the star comes, I'll just play it one more time. You'll see that as the star comes from far away to nearby, it whips around that black hole. This looks just like a comet in our own solar system. Comets start out far from the sun. As they come into the sun, they go slowly. As they come closer and closer to the sun, they suddenly speed up, and then they whip around the sun. And so here it is. You're seeing the same thing that you see in our solar system. You're seeing it on a much grander scale. And again, this is just Kepler's motions. And so from this, we can say that there's a galaxy, or that there's a black hole of several million solar masses in the center of our galaxy. Now here you have probably all heard of LIGO. LIGO is an instrument on the ground where they detect gravitational waves by interferometric methods. But their distances are small, only a few kilometers. Each pipe is only 4 kilometers long. And even if you bounce the light back and forth, you only get a few tens of kilometers. But if you go out into space, now suddenly you can have a much larger baseline. So LISA is not yet gone up, but LISA is proposed to be 3 spacecraft that are maybe separated by 20,000 kilometers. And so now you detect gravitational waves, but on a completely different scale. And so when it goes up, this will be an exciting mission, which you couldn't do from the ground because the ground is just so noisy. Here's a planetary mission. This is from the Global Surveyor. And so you look at the picture on the left and the picture on the right, you see the water erosion channels. We know that there's been water on Mars in the past, lots of water on Mars in the past. And you know this because of those erosion channels. But here, this shiny patch over here is water that's on Mars right now. So not only has there been water on Mars in the past, there's water there now. And so maybe that tells us that maybe it is a good place to look for life. I won't talk much about Corot, but I'll talk more about it and Kepler worked on basically the same method, which is that if a planet went in front of its host star, it would block a little bit of the light from that star. So you have a small eclipse. And so in the same way that when the moon goes in front of our sun, you have a total eclipse, or when Venus goes in front of the sun, you lose a little bit of the light, Venus transit. So here's a transit of an exoplanet from its star. And what Kepler has done is that it has discovered thousands of such planets. We now know that every single stellar system has planets. Before we didn't know that. We didn't know how many planets there were. Now we know that every single stellar system has a planet. And so what this what this shows, this is called the Kepler Origin. And so what this shows is that it shows the variety of planets that are out there. Before that, all we had our own solar system. And in our own solar system, things are pretty easy to understand. We have the sun in the middle, in the center of the solar system. And we have the hot, rocky planets like Mercury, Venus, the Earth, orbiting close to the sun, and then the cold giants like Jupiter far away. But now what we know is that there's so many Jovian planets and larger that are orbiting closer to the sun than Mercury, or closer to their sun than Mercury is to our sun. So how did they get there? Well, most likely what happened is that they formed far off, and then they were nudged by a neighboring star or by planetary interactions to come much closer to their parent star. So let me, with my last slide, what I'll just say is that one of the things that came out of space astronomy is that it's led to a paradigm shift in astronomy, in the way that we think about doing science. Not just astronomy, but in the way we think of doing science. We're now talking a lot more about citizen science, about science being done by people. The genesis of this came with space missions, because space missions are so expensive that you can't think of saving the data for yourself. It has to be shared with people. And so the idea grew up that data are now the property of the public, not the observer, but rather of the public. Maybe the observer has some proprietary time, maybe 6 months, maybe a year, in which they can look at the data and try to understand it. But after that, the data have to become available to the public. And this has gone along with the computer revolution, with the internet revolution, and with the fact that now most scientific results are publicly available. You don't need an expensive journal subscription. You can go to a public site like archive.org and simply get the data. And so this has all led to a potentially to a democratization of science. Science is not necessarily only done by scientists. It can be done by anyone. Some of the more frictionless ways of doing this are things like Galaxy Zoo or Planet Hunters or SETI at Home, where they give you some software and they say, use this software and then send us your results. So that's one way of doing it. Another way, maybe a more challenging way, and this really requires a lot more. It requires a lot more work on the part of the user, and it requires a lot more effort and a lot more knowledge, because this is one of these cases where half knowledge is not good enough. You really have to go deeply and understand what you're doing. But really, it opens up this situation where you can sit at home, as long as you have a computer and an internet connection, and you can do astronomy research. You can do frontier astronomy research. Still not easy, because you have to know so much physics. After all science builds on the foundations laid by others. And so you have to be aware of those foundations, and you have to know how to proceed. But really, we have opened up an area where science does not have to be a full-time occupation. You can come home after working for a long day and relax by doing a little astronomy or other fields, protein research, whatever you want. You can do that at home. So let me end there. And Gopal, I don't know, do you take questions now or?
There is no questions actually, Professor.
Okay.
So I have a question, Prof, that can you please share for the young students that how they can get into this kind of learning and courses, so that they can be like someone like you or some other eminent astrophysicists, scientists. What is actually the way to go into this path? Usually, the students have they don't know the way to go into astrophysics or these kind of sciences. They usually pursue engineering and like normal MSc in physics and something like this. But what are the special things that need to be taken care of while going into this kind of study?
Say, I'm a professional astronomer, and you cannot become a professional without the education. So go through school, and then after school, you do your undergraduate degree, and then you do your PhD. All in all, I did what, 9 years of education after my schooling. And there's no shortcut there. You have to put in that effort if you want to become a professional. And you have to know from an early age. If you choose to go into engineering, especially given the quality of many of our engineering colleges, you have to, it then becomes very difficult to go into science, just because the quality of the colleges is just not very good. So you really have to do, and I'm not going to say which colleges are good. That's not fair on my part. I don't know all the colleges, and it's just not fair. So, but there are good universities. There are good places where you can get a degree. It's very easy for people to do the searches now to find out which are the good places. And so look, if you really do want to do research, not just in astronomy, but in science in general, you have to put in the work. You have to do, depending on what you want to do. If you want to do astronomy, you have to do physics and math in school. You can't do you can do biology also, you can do chemistry, but you have to do physics and math. If you want to do biology, you have to do biology in school. Chemistry, you have to do chemistry. So that much there's no option. You have to do these. Once you go into college, it's better to not go into an engineering college if you want to do science. Go to a science place and do science. But then know that the quality of the faculty is not always as good as it should be. So you have to do your own reading. Start with the fundamentals. The books that I used for my introductory physics were Halliday and Resnick. Go through, and I went through and I did every single problem in those books. Quantum mechanics, I used Kohn-Tanucci. Again, I went through and I did every single problem in those 2-volume books. So there's no substitute for just being focused and putting in the hard work.
So one more thing that I would love to ask, because I have gone through your profile and even through some interviews and videos that you have been already done. So in that one experiment that you have done with the balloons, something I have seen that. So can you insight it a little bit for the students who are watching this?
So what my focus really on is on space experiments, going into space.
Excuse me, Professor. So can you please put up this presentation so that your thing basically works? Yes. Yeah.
So my focus has always been on space astronomy, things that we can do from space. And so we're now building missions that are going into space. But going into space, there's not so many opportunities to go into space. And so we thought we would start a balloon program where we can where the students can get trained in building instruments, building space instruments. And even if we can't send it to space, at least they'll get experience in building the instruments. And this program has actually worked quite well. We can't do much science from the balloons, but they have built instruments. And because of the experience that they get, they're now getting good jobs in space missions around the world. So that was the focus. It was just that we would do instrumentation.
So, so thank you so much, Professor, for being with us. So it's a great honor listening to you, Professor Jayant. Please accept our sincere appreciation for the insightful talk that you have given. It was really interesting and fascinating. And I'm sure that it will definitely ignite young minds towards the study of space and astronomy. And I thank you so much for sharing your time and experiences with us. And thank you for your valuable contribution for the space and astronomy in the world. Thank you, Professor Jain. Thank you so much for coming in my channel. Thank you so much.
Thank you. Bye.
And bye. Bye.